Hello, fellow students and audience. Now we want to demonstrate the effective stress theories. We know the effective stress concept is very important in soil mechanics, developed by father of soil mechanics, Kazakis, and based on these equations. And the total stress minus pore water pressure equal to effective stress. And there are two ways to increase the pore water pressure in geotechnical systems. The one way is to apply the uplift seepage. Another way is to provide citations like earthquake. And when the pore water pressure is large enough, equal to the total stress, and then the effective stress will equal to 0. The consequence would be so-called soil liquefactions. And you can see in this one, before the pore water pressure are large, that's the normal conditions. So the effective stress larger than 0. And when the earthquake comes, the pore water pressure increase and cause the particle lose contact. And then therefore, the building on the top of the soil lose the capacities. Okay. And I want to show you some case examples. For example, this is the liquefactions caused in Japan, 1964. Also, it's happening in Taiwan due to the southern Taiwan earthquake. And you can see the building is tilting or even fell because of the soil, the ground lose building capacities due to the liquefactions. Another example is this manhole covers uplift, also due to the liquefaction effect. And you can think why some case for the building it will sink down, but for the manhole cover it will uplift. We're gonna demonstrate these phenomena using this equipment. What you see here is the first we have the soils saturated loose sand, and then we have a layer of glass beads. And this glass beads is just to prevent the water, when the water go up, to provide a uniform flow, to prevent the jet effect. Also, we have these nanometers. This is to indicate what is the water level, also to measure the pore water pressures, total height. And now, let's for first case, let's provide the upward seepage and see how it's changed the soil effective stress. But before we start, turn on our pump. Let's use this one. I try to punch the soil by this stick. Although you cannot feel, but I just show you before we turn on the upward seepage, the soil condition look normal. Still provide some building capacity. Turn on the pump. We have two pumps. One is small pump, another is a large pump. So before we turn on the pump, you can see the water level in nanometers is all indicated at these water levels. So you can pay attention to the increase of the water levels because this is the most bottom one. And the water level in nanometers decrease because there's a halos when the water go up. Not only the water levels, but also due to the upward seepage, the pore water pressure are increased as indicated by nanometers. And now you can feel the soil become much loose. And it's indicated the shear strength decrease because of the effective stress decrease. And it's become very easy for me, even without too much strength, to punch through into. So how about let's turn on the large pump. Once we turn on the large pump, the water level in nanometers increase further. You can see it's become very high. That means there's a very high upward seepage, very large pore water pressure come from the bottom to the up. And now gradually, if we're waiting for a few seconds, and the liquefactions are gonna occur. Okay, so we can start to see there's a soil pumping, soil boiling occur in here. And now the soil, I totally believe, is totally lose its strength because in this condition, it's just like a liquid. I can stir, I can do anything without any resistance. And this we call effective stress equal to 0 or soil liquefactions. Okay, now we just demonstrate the effective stress decrease due to the upward seepage. And now let's see what happens if we change the seepage from upward to downward. And now the condition is the flow from the top and going to the bottoms. First, I would like to have your attention on the nanometers. You can see the water level now is decreased to here because it's indicated the pore water pressure is decreased, going down. And with these conditions, the soil effective stress increased because of the pore water pressure decrease. And now let's feel how the soil, the soil become much stiffer compared to the case with upward seepage. Again, that's because of the soil effective stress increase due to the decrease of pore water pressures. Okay, now let's look at how the liquefaction influence our buildings. Let's assume we have a 4-story buildings and built up on the ground. And this ground is a sandy ground, saturated sandy ground. Okay, and before earthquake come, there's nothing happens. The building can stand by itself, supported by the building capacity of the soil. And now let's use this hammer and hit the corner of this table to provide some citations into the soils, simulate the earthquake coming. So you can look at what happened to the nanometers, the water levels. Okay, so I hit several times because the earthquake can have several citations. I believe you already pay attention to the water level. During I hit the table, the water level in here are increased. Also, the building collapsed. And the building collapse is not because of I hit the building. It's because of the pore water pressure increase, soil liquefied, and lose capacities. And then this building just collapsed as we expected. I want to compare this building and with these photos from case study. Did you see? Actually, they are quite similar because they are due to the same failure mechanism we call liquefactions. Okay, the first time I hit the table several times to simulate there's a long duration earthquake. And now let me just hit the table one time, but very hot, and simulate there's a big earthquake, but in the short durations. And let's look at what happened. The building even is not collapsed because the duration is very short. I believe you also look at the water level are increased. But maybe you can see all of the building did not collapse, but it settled a little bit because of the liquefaction effect. Okay, so in this demonstration, we show the long duration or large magnitude both can create certain magnitude of damage to your structures. Okay, now I have another toy. This is the plastic bottles and with some steel bits inside to provide some counterweight. And I want to try to bury this plastic bottle inside the soils. And now let's turn off the pump. So the soil condition come back to the normals. And this is to model the manhole under the ground. And let's see what happened when the earthquake comes. Okay, so let me provide several citations, these soils, and see what happened to our small model manhole. Okay, so now you can clearly see the manhole uplift, although it's not totally flow up. These conditions compared to the case happened in 311 Japan Great Earthquake. And you can compare the phenomena we observe from the field and also the phenomena we demonstrate in laboratory. Won't they have the similar behavior? Yes, that is because of, again, the liquefactions cause the damage to the man-made structures. And you will wonder why from the first case for the building tend to tilt or sink or collapse. But in this case, the manhole tend to uplift. Of course, the answer is easy. That's because of the density of your structures. If the density larger than the water, it will going down. If the density smaller, it will uplift by the water. So with that, I hope you can understand by seeing the effect of soil effective stress.